Good morning. So I want to give you a short introduction to MCMC methods, which will be very, very basic. So if you have heard already about MCMC methods, I'm not sure there will be much new. All right, so this is the plan. Hopefully I'll reach the last part where I want to speak about more recent developments on MCMC methods, but I'll start discussing different aspects of the Metropolitan testing algorithm, mention Gibbs sampling, and briefly introduce Hamiltonian Monte Carlo in preparation for Aki Vettari's practical this afternoon, which is about STAN, and STAN is fundamentally based on HMC for Hamiltonian Monte Carlo. All right, so those are the topics I want to cover for the Metropolitan testing algorithm, to try to explain why Markov chains can be used for simulation, and then look at different aspects that are maybe a bit more novel and maybe not. So I think that the fundamental idea about using Markov chains for running Monte Carlo is that when you consider the approximation of an integral by simulation methods, there is no reason to use IID simulations from the target density F. So these are notations. F is a density, H is any integral function. And so an illustration of that is important sampling, that having a sample, IID or not independent sample from G, G being an arbitrary density, is enough to provide an approximation to the same integral if you introduce the importance weights. And actually it's not only a convenience for approximating I without simulating from F, but in all cases, there are G's that do better than simulating from F. So actually, it's even better than simulating from F directly. Well, here I want to talk about using Markov chain. So the other option, or another option, is to produce a Markov chain that is not independent, obviously, that is not exactly distributed from F, but that converges in the sense of the ergodic theorem to the distribution F. And with this Markov chain, it's enough to provide another type of approximation of the integral I, and in many cases, that's the only available option because of the complexity of the density F. And so that's the fundamental idea of MCMC method, that is starting from a certain arbitrary value or from a certain distribution, one produces a Markov chain which is certain to enjoy F as its stationary distribution. And so there is convergence of distribution of the random variable xt, which means that if you take T naught with T naught large enough, then xt naught is approximately distributed from this limiting distribution F that is associated with the Markov chain. In some cases, you can guarantee that xt naught is distributed from F, and then started from xt naught, following the Markov chain from that point, you have simulations that are marginally distributed from F, and the whole, it's still Markov chains, so they are dependent, but for most approximation purposes, that's just good enough. And in ideal cases, you can actually do better than IID simulation if you manage to get the Markov chain to be negatively correlated, which is almost never the case. Now, that's a concept. How do you implement the concept? Well, you have to create a Markov chain that enjoys F as its stationary distribution and its limiting distribution, and that can be simulated in a reasonably easy fashion. And so there are several solutions, but the workhorse of MCMC methods is the Metropolitan hasting algorithm. And here is a picture of Metropolis at Los Alamos in the 50s. So the idea of this algorithm is that instead of simulating directly from the proper transition kernel, the one that is associated with F, you pick an arbitrary transition kernel, which is actually a conditional density Q of y given x, that we call the proposal, almost arbitrarily, and then you turn it into something that fits the target F by a very simple trick, namely that you accept or reject your proposals, just as in the accept-reject algorithm. Instead of simulating from F, you use another distribution G, and then you accept or reject your simulations. Here it's even more basic because there is no restriction on the transition Q. The trick is that by making a transition associated with Q, so Q of y given xt, you keep the possibility to reject this value, and the probability to reject that value is driven by the target distribution F. And so the probability of acceptance of this new value is the ratio of the F's at the new value and the current value multiplied by the inverse ratio of the proposal densities. And so on the top, you have a joint density for x and y, which somehow replaces the actual density for the pair xy, which is at the denominator. And so that's enough to turn the pair x and y into something that is distributed from F for y, as we will see in a minute. So it's very basic in that you have the choice of Q, so you take something that you can compute and you can simulate from at a reasonable cost, and then whatever you produce, you accept or reject according to the target F. And if you reject the value yt, because it gives a too small probability, then you repeat the current value. So xt plus 1 is equal to xt, which, if you recall the accept-reject algorithm, is a big difference, because in accept-reject, you keep rejecting and then you accept some of the values. Here, if you reject, you repeat the current value. And so that's a big difference. Okay. So some of the properties of the method are that, first, you don't need to know F or Q completely. That is, you can miss a normalizing constant, a multiplying constant for both F and Q, and because there is a ratio in the probability of acceptance, any multiplicative constant vanishes in the ratio. So that's something that is fairly interesting in Bayesian statistics, where you can compute the prior, hopefully the likelihood, and you miss the normalizing constant. But even the proposal can be something a bit involved and also miss the normalizing constant, and that doesn't matter for the probability of acceptance or rejection. Okay. And then obviously you never move to points where F is 0. So if f of yt is equal to 0, you reject automatically. But that doesn't mean that you shouldn't use a Q that leads to regions where f is 0. So that's a plus in that you can make proposals that are outside the support of F. That's not very efficient because automatically you're rejected, but that allows for easier choices of Q. And so, for instance, if Q is a normal distribution and if F is supported by the positive real line, it's not a problem, the algorithm is still valid. It means that each time you propose a negative value, you reject, and so you keep the current value. But the algorithm is still valid overall. Okay. So that's an important thing. As opposed to IID sampling, your Markov chain allowing for the repetition of the current value means that you can find several times the same numerical value in your simulations. And that's not incorrect, it's just a feature of having this Markov chain. And the last point that is marginal here is that if you look at the YTs, so there are YTs that are generated at each iteration, the YTs usually do not constitute a Markov chain. And the pair XT-YT is a Markov chain, but YT is not, most of the time. But that can be useful for other properties. Okay, so why does it work? Well, it's very simple. It's just the choice of this probability of acceptance validates the method in the sense that the Markov chain that you produce by the Metropolitan algorithm enjoys this balance condition. That is the Markov kernel, K, which is not Q, but K, the Markov kernel of the entire step of simulating and accepting or rejecting, as this symmetry that F times K is symmetric in X and Y. And that implies immediately that F is a stationary, because if you integrate both sides of the equation in Y, on the left-hand side, you get the distribution after one step starting from F, but on the right-hand side, you integrate in Y, so K vanishes because it's a probability distribution in Y, and therefore you get F of X. That means that after one step, you are again distributed from F. So F is stationary. And it's stronger than that because thanks to this detailed balance property, you get a reversibility of the Markov chain, which means it has the same properties going forward in time and backward in time. And because F by design is probability density, the chain that you produce this way, provided it is irreducible, is positive recurrent with stationary distribution F. Okay. And then in addition, if you have a positive probability of rejecting the current value, so if you are not moving all the time, then you can stay once at the same value, so that the chain can repeat once or several times. That implies that the chain becomes aperiodic, and therefore it will converge to the distribution with density F. Okay, so those are Markov chain basic properties that validate the method as a simulation method. Yeah, irreducibility is a bit of an issue, so you can, if you pick a proposal Q that is too narrow in scope, so for the support being too small, you may fail to reach the entire coverage of the density F, and then the chain is not irreducible, it doesn't visit the entire space. But if you can push Q to be wide enough and reach far enough, then you get irreducibility. And then from there, we get what we are interested in, that is, you have an ergodic theorem that is the average of the h of xt's as a chain evolves a long time is the integral of h against the density f. And so just as in regular Monte Carlo approximations, the average converges to the integral, almost surely. And the distribution of the chain at time n, this is the second result, will converge to F according to different measures like the total variation norm. So that's, in a nutshell, the reasons why you can use Markov chains to run simulation. You get essentially the same properties as IID simulation, at least on a rough scale. The details are about how efficient this method is, both in terms of producing the Markov chain and converging to the limit, because here it's only an almost sure convergence result. Well, in most cases you will get a central limit theorem, depending on the function h you try to integrate, and then the difference would be in the variance, in the asymptotic variance of the central limit theorem that will compare mostly defavorably to IID sampling, but essentially you have the same speeds, which is a comfort. So let's look at some versions of the Metropolitan algorithm. There is one that is mostly interesting to understand the connection with accept project. So if Q is a conditional density that doesn't depend on the previous value, so I write it G, then the acceptance ratio writes as F over G, just as in accept project. The difference is that you don't divide by the maximum of F over G, but the previous value of F over G. So it's like a poor man accept project, and still valid in this MCMC sense that while you are not using the right constant in accept project, by looking at the sequence of xt's, overall, you do get convergence to F. It's only valid once when xt is the argument of the maximum of F over G, in which case you move to that value because F over G would be the maximum. But except for that specific value of xt, it's moving faster in that you don't divide by the maximum. So, of course, it's not an IID sampling method, except if F is equal to G, which is not a case of interest. But if you are in the same situation as accept project, where F over G is bounded, then the convergence occurs at a geometric rate that is independent of the current value, and that is driven by the constant m. So it converges as 1 minus 1 over m to the power n. That's geometric ergodicity. And where is an example on observing the square of an AR1 model. So you get this sequence of xt's, that's your observable, and you're interested in the parameters sigma square and tau square, but you need to reproduce the hidden sequence xt, it's a hidden Markov chain. Then if you look at one of the xt's, you have this distribution that is a bit of an issue because of the square, and so instead you can make a proposal G that is a normal centered on averages of the previous and future values, and the ratio pi over q is bounded in that case because it's less than 1. And you can run the chain by making these normal proposals and accepting and rejecting. And here is a picture of 500 simulations of an entire sequence where you have horizontal features that are due to the rejection of a lot of proposals. So it keeps rejecting for dozens of iterations before moving to other values, and sometimes it jumps a lot, and that's due to the target being bimodal in that case. And although it doesn't look like a very nice mixing sequence, in terms of reproducing the target, as you can see on the picture, you do get an histogram that is quite compatible with the target. But of course, that's not a very common choice for the proposal to make it independent, because you don't know enough about the target in most settings. And so the proposal is more likely to depend on the current value, and the generic choice for the proposal is a random walk, where you take the current value and you perturb it a little bit, so you add an epsilon t to xt, and you look at this new value to see if it's still near interesting values for the target f. And so now G denotes the density of the noise epsilon t. And if you assume that G is symmetric, that simplifies the acceptance probability in the algorithm, because G vanishes thanks to the symmetry. And so you essentially consider your new value yt directly through the value of f. So the probability of acceptance only depends on f and not on G. Of course, this is not to say that G has no importance. I mean, its scale will drive the efficiency of the algorithm, but in the acceptance, you only look at relative values of f of yt and f of xt. That is, if you go higher on the density, you will accept with probability 1. If you go lower, you will accept if you don't go too low. Okay. That's how you move on the surface of the target density. And well, that's one proposal that you find in the historical paper of Hastings. Like, I mean, it's a toy problem simulating a normal. You can use a uniform that has a smaller support compared with a normal, but because it can move anywhere in a finite number of steps, that produces still an irreducible Markov chain. And well, the probability of acceptance in that case is directly given by the normal density, because the proposal is symmetric. When I say uniform proposal on minus delta delta, this is a distribution of the noise, of course, that you add to the current value. But then you can use the method in much more realistic examples as, say, a mixture posterior distribution that Guillaume mentioned yesterday. So if you have a distribution on theta that is of that format, that you can consider as a complex distribution, well, you can move all the parameters of that mixture according to a random walk. A very simple one, well, you should actually scale the noise by a scale omega, so that you move with a large enough frequency. And then, I mean, this is a bit of a black box as a target. This pi of theta given x is not something that you can make sense directly, but if you just compute this density at the new value over the density at the current value, which is feasible in a reasonable time, then you move or you don't move with a certain probability. So that's computable, and you can very blindly implement this algorithm. Then you have a few cranks to turn to make it to make the acceptance rate reasonable, but that's still feasible, and you get with this random walk a prediction of the posterior distribution in a rather complex space. Like here, it's a mixture with 3 components, so you have 9 parameters. And you do recover the marginal distributions of the different parameters of the normal mixture, for instance. Okay. And that's another example that is closer to Julien's example of yesterday, that in dimension 2, if you have a mixture with 2 means unknown, and I started from the cross here, the algorithm, Well, there are two modes in that example for that data set, but the random walk walks around the first mode that is low and reaches the high mode of the target in a certain number of iterations. Here it's not representative of how long it has run because a lot of values have been rejected, so you only see the accepted points. So I think there are at least 1,000 iterations, maybe 5,000 in this picture. And another example I skip. The random walk algorithm is like the default choice for metropolis testing. It cannot enjoy very strong convergence probability in the sense that since you move from the current value, if you start very far away from the region of interest, it will take time to reach the region of interest, much longer than if you start from the region of interest. So you cannot get uniform ergodicity, that is a convergence that doesn't depend on the starting value. It will always depend on the starting values. At best, you can prove geometric ergodicity if your target has thin enough tails. And if it has not, that's an example taken from Hennenfent and 3D, you do get a rougher convergence to the target as shown by this comparison of the envelope of the average converging to the same value. And if you take a target that has fat tails compared with your proposal, it will take quite a while to recover this proposal. So this is an example of a Cauchy simulated using a normal noise, and normal distribution has thin tails, so it takes quite a while to get to the Cauchy. You don't see that so much on the histogram. That seems to fit not so poorly. I mean, the tails are recovered, but you can see that in the envelope of length of the Markov chain. So I did 500 Markov chains in parallel, and this is the envelope of the sequence. It's not producing something highly stable in terms of envelope, as you could expect. So it's not a very efficient way of simulating a Cauchy, obviously. Then there is a deeper literature I will not cover here about finer convergence probabilities, including the central limit theorem. There's a range of conditions for the central limit theorem to apply. But it's very close to the IID case in that there is a Lyapunov condition, for instance, that it is sufficient if you can reach a certain set with a finite probability, and that's what we call horizontal conditions, like the one in the middle, where the average of the function up to a renewal time is finite, which is a bit hard to establish. There are other ways to get to the CLT when there is reversibility of the algorithm if the asymptotic variance is finite, for instance. So there is a literature where with some efforts you can prove deeper types of convergence. All right, so to keep moving, let me introduce a few extended versions of async metropolis algorithms. Not the reversible jump, but Langevin and Hamilton and Monte Carlo, which is not exactly async metropolis, that's a different H. So I mean, the Langevin algorithms are based on a continuous time diffusion, which enjoys f as it's stationary measure. That is, if you are able to run this continuous time diffusion, where bt is a Brownian motion, and nabla log f denotes the gradient of log f, then this diffusion would have f as, well, its stationary measure in a rough sense. And of course, you cannot do that in continuous time. So if you discretize the diffusion, you get a sequence with discretization step sigma. And well, this is, if you think that sigma is very, very little, that's almost like running continuous time. But in that case, the chain is not necessarily recurrent. So if, well, you have this condition, so if sigma is still too large, you do get a transient Markov chain that is not enjoying f as is stationary because it goes to infinity almost surely. And so there is a version of this proposal that still works, that is called MELA, for metropolitan correction to the Langevin algorithm, namely that instead of moving continuously according to this sequence, which is a random walk with this drift induced by the gradient, you can reject some of the values. And so you're back to metropolitan with this proposal suggested by the diffusion, and the acceptance probability is exactly the same as before. You have the ratio of the f's multiplied by the ratio of the proposals. And this is completely valid because that's a special type of metropolitan algorithm that enjoys usually better properties than the basic random walk proposal. And the scale sigma, which initially was the discretization unit, can be reinterpreted as the scale of the move, and chosen so that you have a certain acceptance probability that in some cases has been proved to be 0.574 for being optimal. I mean, there is a whole collection of results in that spirit. Now, that leads to this quick mention of the acceptance rate. What is the acceptance rate? This is the average probability of acceptance of a metropolitan algorithm. And if it's very large or very small, the algorithm will not be particularly efficient. And when you can manage to calibrate your algorithm to reach a certain acceptance rate, there are methods to aim at given acceptance rates that are, again, proved to be the optimal ones. And that leads to adaptive MCMC that we'll mention in a minute, just to show the impact of the acceptance rate and the calibration of the scale. If you choose a scale that is too large, you get a lower acceptance rate, but you may reach farther regions of the target. And if, on the opposite, you choose a scale that is too little, you may miss some targets. So this is the same example as before, the AR1 with noise that is squared. This is a snapshot of the evolution of the Markov chain, which, as you can see, is mixing reasonably well. Very few flat lines on the picture, and the fit of the target that you can plot on top of the histogram is extremely good. That's a scale of 0.1. But if you move to a scale of 0.5, you get this picture for the Markov chain that is less appealing because it doesn't move much. It stays with the same value very, very often. But then if you plot the histogram against the target, then you realize there is a second mode that is actually the largest one, and in the previous simulation you were stuck at the wrong mode. So the choice of the scale is important, and high acceptance rates, as in this picture, are not necessarily meaning that the chain is converging correctly to the target. Here you essentially have missed the target out of 10 of 100,000 iterations. While here it moves slowly, but it mixes enough to cover both modes. And what makes the difference between the two pictures is the choice of the scale. A few remarks on a reinterpretation of the Metropolitan sequence for simulation purposes, for better approximations of integral, and that fits under the head of what's called localization, which is the use of conditional expectations to improve on the variance and therefore the efficiency of the estimators. So when you look at this Monte Carlo approximation to the integral of h, that is the average of the h of xt's, you can actually look at the different values in the sequence of xt's that I denote zi. Okay, so zi is made of the accepted yj's, and xt is always one of the zi's a certain number of times. So zi is repeated ni time, ni being 1 or larger. And so the standard Metropolitan estimator is a weighted average of the accepted yj's. Okay. So that's exactly the same method, it's just a way to look at it. Okay. And so if you look at the zi's, they are themselves Markov chains as the xt, but with a different stationary distribution, which is actually q tilde. And q tilde is q multiplied by the acceptance probability, the alpha zi, divided by the average of alpha times q. So the stationary distribution, the transition is not the same, and therefore it has a different stationary distribution, which is pi tilde made of pi, the target. It's no longer f, it's pi times p, p being the average acceptance probability for the move from zi to a y. Okay. And you can prove that it is a stationary distribution by the detail balance condition. So you get symmetry in x and y here, and therefore you get pi tilde as the stationary distribution. And so this accepted chain has different properties, and realized sequence of xt's is still a Markov chain. The number of repetitions is independent of the next value, because you keep accepting depending on zi. Ni is a geometric distribution. That's a very simple property with acceptance probability p of zi. And as we saw, the Markov kernel is this q tilde, which is a different target, and because p of zi is usually not available in closed form, that's a sort of intractable stationary distribution. But again, everything is done as a byproduct of the regular Metropolitan algorithm. I'm not changing anything in the algorithm when I look at it that way. It's just another way to look at it. And why is it interesting? Well, it's because there may be a way to recover a better estimator with the same simulations. And that's in the aside I want to talk about. If you look at the average produced by the Metropolitan algorithm, it weights the h of zi's by this geometric random variable. And in a sense, that's noise. You create the zi's, and then you make more noise by making a geometric number of rejections before moving to the next value. So something that would have a better performance, that would have a smaller variance, is this estimator where the noise of the geometric is removed and replaced by its expectation, which is 1 over p of the die. Because that's one noise out of the two. You keep the noise of the zi's and you remove the noise of the ni's. Okay. And well, because you may be missing constants, you could divide instead by the average of the p of the di's. Or again, it can be written as pi, the target, over pi tilde, which is the actual distribution of the di's. Okay. But there is a caveat in this idea, which is that p is almost never available. And if it was available, you could as well compute the integral of interest. So that's not working. And the ni's are the first idea to evaluate the 1 over p of the die. So we are back to stage 1. Is there anything better to exploit in this idea? Well, one way of writing ni, which is not maybe the most natural one, is that it is 1 plus the infinite sum of the products of the indicators that uniforms are larger than the accept probability. That is, you are at zi, and you keep producing YLs from Q, and you keep rejecting, well, until you accept. And this sum is telling that, well, up to a certain value of j, you have been rejecting the YLs. And once the integer is 0, every further term is 0. So this infinite sum is not that frightening because it stops at some point, which is when the chain moves to the next value. Okay. And so if you can get some noise out of this indicator, of this product of Bernoulli variables, then you gain in terms of variance. And one way of reducing the noise is to replace the indicator by its expectation, which is 1 minus alpha. And the uniform is larger than alpha with probability 1 minus alpha. And so that one is an unbiased estimator of 1 over p of the die, which of course brings a reduction in the variance of the Monte Carlo estimator. So the only point is how to produce this evaluation while you keep simulating the YLs until the term is 0, which means until alpha is equal to 1. And then you get an epsilon, xi I, that is a replacement of the ni. Okay. And so that's a kind of localization because you do reduce the variance. And if you're really afraid that your simulation may go forever, you can actually stop at a finite horizon and then stop and repeat the next point, but you will get a reduced variance. Another point about Metropolitan testing, so it's another remark, is about big data. If you have a lot of observations, so a large number of observations, and even if you are not in a totally intractable likelihood setup, computing the likelihood as a product of densities of the xi's will take order n time, because we assume it's not a very standard distribution where you have sufficiency and a sufficient statistic that is faster to compute. And so each time you get a new value of theta, you have to compute this product, and therefore you have a time of order n to consider the next value. So in the recent years, there has been an attempt to try to get around that difficulty of large samples and costly likelihoods, which are one way or another of taking observations out of the picture, so working on subsets, either taking advantage of parallel abilities and producing different MCMC outputs on different processors or computers, and then merging those different samples together at the end, or essentially keeping a subsample at every iteration of the algorithm and either correcting or not correcting for this subsampling. For instance, using this pseudo-marginal ID, I should be able to mention in a few minutes. There is one possible way of improving the computing time, which is to look first at a subsample, and then if the proposed value is not good enough, to reject it immediately, and if it seems good enough, to accept or reject it with the rest of the sample. And going in two stages, gain time, at least in the rejection part. In the acceptance part, you don't waste much time, but if you reject early, this delayed acceptance ID, that you will gain time. And this method of therefore looking at a subset of the acceptance probability will produce a faster moving chain just by removing some of the observations. So the notion of delayed acceptance is one way of trying to fight this big data problem by looking through the chunks of the acceptance probability one by one and rejecting as early as possible, unless all parts are accepted, and then you move the chain. And if you block the observations in such a way that the costly terms are occurring at the end, then they are computing less often, and you gain time in moving around with a Markov chain, or not moving around, because it's actually when you reject that you don't compute them. And this method is actually found in the literature as early as 97, when Fox and Nichols proposed an acceleration method by replacing the true acceptance probability by a cheap approximation, and then validated the method by regular ways. So this is completely valid. It's just that you generate several uniforms instead of one, and in the end you are still distributed from the true distribution. Now, it's not a completely perfect issue to the big data problem, in the sense that at some point all the terms have to be computed. And as I mentioned, there are other solutions that are more of the pseudo-marginal flavor that move faster, but with more variability in the approximation of the acceptance probability, and therefore some issues at convergence as well. I mean, speed of convergence. Just one mention that is useful, I think it's that if you try adaptive MCMC, that is, if you keep changing your transition kernel, your proposal, according to what you've seen so far, you may get into trouble. Because if you try to fit your proposal to your target. All you know is what you've seen so far in the simulation. And therefore, you're producing a transition that is no longer Markovian, but that depends on the entire past. And therefore, this crashes the validation of the original algorithm because it's no longer Markovian. So to prove that it converges is a much harder challenge. So just one example and a few pictures of what's called a PolyT distribution, which is a product of T densities. So the target is this product of the news plus xj minus xi being the quantity to be simulated. And one early notion in MCMC literature was to try to say, well, we have seen this simulation so far. They are giving us an approximation of the mean and variance of the target. What about using normal centered at this mean with that variance? Because that's, if it's converging, is close to the target. And let's pretend it's like an independent proposal. Okay. Well, if you do that, you see very quickly that it doesn't work and doesn't converge to the correct target because there's a long-range dependence, and that may collapse to a very small value of the variance if you start with a small sample at the beginning. And even a bit more advanced and creative ideas on finding a proposal that is, say, a non-parametric version of the target doesn't work. So the target is a red curve, and the histogram fails to cover correctly this target. Even starting with a large enough sample, and that's, I think, the non-parametric version. It will be more concentrated than the target. So doing adaptive MCMC is a bit dangerous. You have to keep decreasing the adaptivity as shown in some results in the literature. Okay, so that's a bit of a quick tour of Metropolis Hastings. That remains the basic default choice before moving to more advanced proposals like Hamiltonian or PDMP. Before that, I want to make a few mentions of Gibbs sampling that is a bit of a special case in the MCMC zoo, in that it came in earlier or at a different time than the other methods, at least in statistics. And it has interesting feature that you can recycle when considering more advanced MCMC algorithm, in that it is a way to kill the problem of the dimension, which is, I didn't speak of the dimension here for the Metropolis Hastings algorithms, but of course, as the dimension increases, to have a proposal that fits all dimensions and still preserves some efficiency in the exploration of the target gets more and more difficult. So the curse of dimensionality also hits Metropolis Hastings algorithms. And one way of getting around this difficulty of the dimension is the Gibbs sampler. So even with more advanced techniques, to break the dimensions into smaller bits by Gibbs sampling maybe a good idea. So I mean, it starts as if it was a very special case that we can only use in very specific situations. But as we'll see, it can be generalized to become almost a generic MCMC algorithm. So the starting point is that if you have a target f to simulate from in dimension P, you may consider the full conditional densities associated with F, that are F1, F2, Fp, and move the Markov chain one component at a time. That is, you change xi according to the full conditional of xi given the other components of the vector x. Which means that after p steps, all the components have changed. There is no notion of rejection here, so all the components have changed. And so p steps of these simulations bring you a new vector x. Okay. So that's the algorithmic representation. And this Markov chain, because it's a Markov chain that doesn't change very, very fast, but it keeps changing. This Markov chain has convergence properties such that F is the stationary. And that's very easy to prove, because if you start with X from the distribution F, every one of those P steps keep F as the stationary because you use the correct conditional density. So you're not getting away from F at any stage. Okay. And then this is a nice way to get around the dimension, because you don't have issues with simulation. You are simulating from a given density, which is the right one, quote, and you produce simulations in dimension 1, so you don't have to worry about large dimensions. Of course, it's over the P. That means that to create the new vector, it takes something of order P. Other property is that it's not a reversible method. It's a combination of reversible steps. So reversibility, if you want to achieve reversibility, proceeds by turning this range of simulations into a random sequence. So either you pick a number at random, or you pick a permutation of 1 to p randomly. And then you recover the reversibility that you may need for the central limit theorem, for instance. So, I mean, it works as simply as when you try to find the maximum of a function. You look at the maximum in one direction, you reach this point, then you change direction, you go to another maximum, and you keep doing that until you cannot move higher. And so you have found the local maximum of your target. When you do simulation, it's about the same. You keep simulating from in each direction, which makes a very spatial pattern of the moves. But if you look at every p move, then it goes from one place to another in the parameter space, and you do end up with a cloud of points that is representative of the target distribution. Now you can do that in dimension p. If you are in dimension 1, it's not such an issue, because you can create other dimensions by looking for auxiliary variables or latent variables. And one way of creating latent variables is just to imagine a joint distribution G such that the complicated target F is the marginal of that joint distribution G. So I call that demarginalization. It is a distribution such that it's marginal, it's F. And there is no reason for that to have any meaning for the original problem. It's a creation that is abstract and possibly totally artificial, that produces F as its stationary. So there is no reason to make sense of Z. Z doesn't exist between quotes. And so if you move to this new problem, that's a basic principle for simulation. If you can generate pairs from G, then marginally X will be from F. So simulating G creates as a byproduct simulations from F. And so you just copy and paste the previous slides, but replacing F with G, and the outcome is a simulation from G with the side product of the x's being simulated. Just, I mean, without going into the details, there is a wee problem with GIPS, namely that it's maybe a bit poor in energy when exploring a target. And so here is a picture we have seen already, or yesterday and earlier today, of the posterior of a mixture with two unknown means. If I start a GIPS in this setting, there is a completion to make it run easily by associating with each observation the component it comes from. So that's something you may have seen with the EM algorithm. That's exactly the same idea. You allocate observations to one of the two components, and once you have two subsamples, one for each component, you get very simple distributions to simulate from. So you move there, and then you complete, and you move, and you complete, and you move. So it's like EM, except it's random instead of maximizing. Well, if you start from an arbitrary value on this surface, which I think is somewhere here, we do get a very quick convergence of the GIPS sampler to the mode of the target. But if you start instead at a point that is near the second mode, so it's here, then in that example, the GIPS sampler has really strong difficulties to leave that mode, even though it is smaller than the other one. So, I mean, that's a picture in the log scale. If you get to the regular scale, this mode vanishes from the picture. But without any modification of the algorithm, and when compared with the random walk I showed you earlier, the GIPS sampler will not leave that mode and be stuck at the wrong mode. So it's irreducible in principle, and you can prove that this is a very simple case by simulating the allocation of the observations to different modes. You are in an irreducible distribution, but in practice, there is not enough time to watch for the move to the other mode. So that's a problem with GIPS, that it has low energy to move around, and if you have a multimodal target or a very narrow type of target, it will take a while and sometimes forever to reach stationarity. Meaning that you have to find alternatives or band-aids to solve this problem, and one is to use tampering that I will not mention here to lower the gap between the modes. So there is something called parallel tampering, where you take this target to a power less than 1, and that flattens everything on the surface, and that allows GIPS to move more easily between the modes. Which in this example is essentially the same as subsampling the observed sample and creating this new target with less points in the sample, which means that the modes will be less separated and the GIPS will move more easily. And in the end, everything ends well, and you get an exploration of the target. Something I want to mention is the size sampler, because that's a form of generic GIPS. And well, it relates a little bit to something of the first section with the indicators, which is that if you have a statistical problem where your target is a product of individual likelihoods, you can replace each of the FIs by an indicator that an omega I is less than Fi. That is, if I integrate the second equation in omega I do recover the first one. And so this is a way from scratch to create an auxiliary variable, which is a vector of the omega i's, such that your original target is a marginal of the second target, the augmented target. Okay. And so that's called slice sampling, in that if you aim at the second target, that is a uniform in this abstract collection of omega i's, then marginally you do recover this as your target. And so that should make life simpler because it's a uniform. So that means that you run a Gibbs sampler in this setting, you repeat simulations of the omega i's that are uniform, so it cannot be simpler if you can manage the computation of F1, F2, Fk, and then given the omega i's, you generate a Y that is a uniform on the set restricted by the fact that Fi of Y is larger than omega it at the current realization of each of the omega i's. Okay, so it is the intersection of those slices of the parameter space, because theta is my parameter of interest. And of course, that's hiding the difficulty under the carpet, because that's the difficult part. To simulate from this set, if it's not of a nice shape, may be difficult, very difficult, or impossible if there are many slices and the FIs are really complex. So it doesn't, in practice, it's not always feasible to implement this algorithm. But at least on the paper, that's a generic method that may be attempted for simulating from F. So here is an example in the tail of a normal distribution. So it's a normal -3, 1 truncated to 0, 1. So you cannot wait for the normal to be larger than 0. It takes forever. So if you simulate in that tail this type of slice sampling, you just need one slice. So you have one omega that is uniform over 0, F being the normal distribution. And you keep moving horizontally and vertically, horizontally being the x, vertically being the omega. And after a certain number of iterations, you have actually covered the entire space for the target. So you have mixed well enough to have a sample that is equivalent to an IID sample from this truncated normal. And in that case, you can prove very high performances like uniform ergodicity. But that's a general feature of the size sampler. If you can manage to implement the size sampler, the fact that you work on uniforms, they are on bounded spaces necessarily, that implies fairly good theoretical properties. And so, for instance, if your target is bounded, the space is bounded, the size sampler is always uniformly ergodic. Okay, so you just, no matter where you start from, you reach any point in the space with a time that doesn't depend on the starting point. The problem is more the implementation to find a slice where you can simulate uniformly. The property of the Gibbs sampler, as I mentioned, is if you get irreducibility, the fact that you use the right target means that, conditionally, means that you have no issue about stationarity. The Markov chain has F as its stationary distribution necessarily. The only problem is irreducibility, because it's not true that if you can simulate from the full conditionals, you will reach any part on the support. I mean, if the support is not connected, for instance, you may end up on one connected component of the support and never leave that connected support, component. So irreducibility is really something you need to check when you run the Gibbs sampler. But if this holds, then you recover exactly the same properties as previously, of convergence of the ergodic average and convergence to the stationary measure, assuming you have aperiodicity, which is a minor detail. And then the size sampler, again, as I mentioned already, is given further properties, although it's a special type of Gibbs sampling, that under some conditions it is uniformly ergodic. Now, you may wonder why this Gibbs sampling is working based only on full conditionals. But actually the full conditionals, if I give you all the full conditionals of a distribution, you do recover the joint distribution. I mean, it's not the same thing as giving you the marginals, which are missing information, obviously. The full conditionals are completely informative about the joint distribution. And so, for instance, if you have a bivariate target, T of y1 and y2, then I can write the joint only through the full conditional. That it is G2 divided by the integral of G2 over G1 in V, which is the marginal in Y1, or the inverse of the marginal in Y1. Okay. So mathematically, I have this equality, and it means that I can write the joint from both full conditionals. And there is a general result that tells you the same thing that's the Hammersley-Clifford theorem, which is that the joint distribution up to a constant happens to be proportional, so the proportionality constant, to the product of the ratios of the full conditional. So if I have a permutation L of 1 to P, and I look at the ratio of all full conditionals at YLJ, divided by the same one at a Y prime LJ, which is a fixed value that is arbitrary. And if I keep moving the Y prime in the conditioning from your right to the left, so from your left to the right, I keep conditioning by more and more of the y's as j increases, then I recover g. And you can prove that fairly easily by substitution. So again, I have a functional representation of the joint based only on knowing the full conditionals. There is just a little caveat to this expression, which is that this must avoid divisions by 0, and so it means that for a given y prime, there must be at least one y prime for which all the denominators are different from 0. And that's called a positivity condition. So this theorem doesn't hold if the support of the joint is not the product of the supports of the full conditionals. That is, the full conditionals have the supports that vary. So for instance, if your support is made of two squares that do not cover one another, you cannot write this for all y's. There is always a denominator that is 0. And historically, it's interesting because it was established by Hammersley and Clifford in Oxford in the 70s, but they never published this result because of the positive condition. They were really seeking a result that would work in all cases, and they didn't manage. And it's only in the later that Julian Zigzag came with a more generic version where if the support was connected, then you could follow a path from y prime to y where all the denominators were non-zero. So it's a more clever design where you avoid division by zero. And so that's a bit of a trivia, but at the same time it's important because it's connected with irreducibility. That is, if you cannot write this theorem for all y's, then you may face irreducibility issue with Gibbs. So that's a problem. Again, localization in the picture, because Gibbs sampling is often a completion algorithm seeking auxiliary variables. There is one of the components that is more of interest than the others, so y1, say, for approximating the integral. And so the side simulations of y2, yp may be considered as useless, except that these extra auxiliary variables can be recycled to lead to a continual expectation, so it should be an E and not an I. That is, instead of looking at the average of the y1t's, you can look at the average of the conditional expectation of h of y1 given y2, yp, and this lowers the variance of your estimator. So if this can be computed or approximated, you do gain in efficiency. For a given term. And you cannot prove that the average has a lower variance because the terms are correlated. So you have to be a bit more careful than I seem to imply. But I mean, in some situations, you can prove that the variance is reduced. So this is an example where I don't know why the expectation became indicators, but if you can manage, well, in this toy example, to replace x by its expectation given y is rho y, and therefore the variance is reduced by a factor of rho. And here is another toy example again of a Poisson with a gamma prior, where you can compute the expectation of lambda given the xt's, and well, you get another format that is actually more efficient than the original one. A remark that is, I won't go into the details, but that is useful for approximating the Bayes factors, so the evidence in Bayesian statistics, is the non-parametric Rao-Blackwellization. And when you run Gibbs and with these full conditionals, there is a side property that is quite interesting, that is the average of the full conditionals is converging to the marginal of that quantity. That is, if you are interested in yi only, you have simulated the yj's, the yi given the yj's, and if you average this full conditional for all your Gibbs simulations, this will converge as t grows to the right marginal. And so you get almost for free a non-parametric estimate of your marginal density that is actually converging at a parametric speed. when I say almost for free, I say it's fairly costly because it's of order T, so it involves all your simulations. So that's not exactly free, but a kernel estimate would have the same type of cost anyway. One last point about the Gibbs sampling algorithm is about improper priors. So in Bayesian statistics, you are allowed to consider improper priors, that is, prior measures that are not probability densities, measures that have infinite mass, provided your posterior distribution is well defined, that is, the likelihood is integrable against such priors. Because it's a matter of free normalizing and conditional on the observation, you have a proper distribution when you consider the posterior distribution. But if you use improper priors and MCMC, you may find yourself in the situation where you have standard distributions for your conditionals. Therefore, you can simulate them fairly easily, but there is no joint distribution because there is no posterior. The prior is so improper that the likelihood doesn't integrate against that prior. And this is very easily found in the literature, that you start running down all your conditionals. Gibbs is very helpful for that. So you have exponential families as your conditional distributions, and it's a one-line code to run them. You look at your sample, they just have a very stable behavior. They give you nice histograms, but actually there is no joint posterior. So you have run something that should not exist. And if that's an issue with a Gibbs sampler, it's an issue with the non-existence of a stationary measure. Okay. So here are two examples. One that is rather obvious, so you should spot the difficulty if you run this code, because the chain will start moving to very large, very small value, more and more, until you get out of the limits of your computer. If you consider an exponential with scale x2, another one with scale x1, or inverse scale x1 and x2, those are two perfectly well-defined conditional distributions. But in that case, if you look at the corresponding joint density, you apply Hammers-Lexie forward, you find that your joint is exponential minus x1, x2. And this density doesn't integrate to a finite value on 0 plus infinity squared. So these are well-defined conditionals, true probability densities, but there is no joint probability density. And so the Markov chain that you will create cannot converge to a probability density. And in that case, it will be a null recurrent Markov chain. So it will be recurrent, that is, it will come back to 0, but it will go to infinity first, and it will take an infinite time to come back. So for simulation purposes, that's not particularly useful, because you don't recover the ergodic theorem and the stabilization of the averages, for instance. Furthermore, for Bayesian purposes, it's not good because there is no posterior. So the object that you're trying to use for inference has no validation. You cannot choose an improper posterior for Bayesian inference. Here is another example that is more statistical and found in the literature, which is the one of the improper random effect model. So you have a random effect model, which is an analysis of variance, with alpha I being a random effect centered at 0, And so you have as parameters sigma square, tau square, and mu. And well, the lazy choice of a prior is to take this Jeffreys improper prior 1 over sigma square, tau square. Because mu is a location parameter, sigma and tau are scale parameter. So that will be my choice, okay. And from there you take this very simple prior, 1 over sigma square, 1 over tau square, you multiply by the likelihood, and everything unfolds very nicely. That is, the alpha i's that are unobserved are normal, conditional on the data, the mu is normal, sigma square, tau square are inverse gamma. So this can be, each of them can be simulated immediately, and this runs very, very fast and very easily. And if you look at the plots, I mean, this is one I made, but you find the same one in the paper, you find very stable features for the Markov series. So this, what is that? This is, I think this must be mu. This is mu, I think. And you can run it for thousands of iterations and you find this feature. So there is no way, when looking at the outcome, that you realize that this is not valid because those full conditionals do not correspond to a correct join. There is no join distribution on the collection of alpha i's, mu, sigma square, and tau square. The Markov chain that has been simulated is either non-recurrent or transient. In that case, it cannot be positive recurrent, it cannot converge to a distribution. And that's a statistical issue. This outcome is not something that you can really trust for inference. And that's a simulation issue as well, because in this example, the outcome doesn't tell you something is wrong, simply because the fact that the integral is infinite, the integral of the posterior is infinite, is due to an explosion in the neighborhood of 0 for sigma square or tau square. You can prove that the posterior doesn't exist by integrating and looking at sigma square. And so this proximity to 0 is such that, well, for programming reasons, a representation of real numbers being with finite number of digits means that the Markov chain never gets close enough to 0 to see this explosion. And so the transience is not visible in the simulation. So you could say, well, it doesn't matter then, but you are still simulating from something that doesn't exist. So, and to mention that even the best ones can fall into this hole. This was actually an example in one of the very, very first Gibbs sampling papers in Hennenfent, Smith, and others, so in 1990. So this is something that you should be wary about. It's very rare that this happens, that you don't see anything wrong. It's more like your Gibbs sampler doesn't seem to converge, and you recheck your conditionals, and you don't see any mistake, and you understand. And the reason actually behind that it's a posterior that doesn't exist. So you should be able to spot it and realize that this is a question. Okay, so let's make a few comments on Hamiltonian Monte Carlo, mostly to introduce Aki's session this afternoon. So this is a more recent at least in the statistical community, a more recent version of Markov simulation method that starts from a continuous time process rather than a sheer Markov chain. And as the slide sampler, it uses an auxiliary variable that it brings on top of the variable to simulate theta. So there is this script plus theta on top of the regular theta with an auxiliary or artificial target that is omega bar of script theta given theta, with the only condition that the marginal of the joint is the target of interest. So far, not much of a difference. And what's called the Hamiltonian is just the logarithm of this joint, or minus the logarithm of this joint. And the way to simulate from this joint is to start with a time process that evolves according to the system of differential equations, where theta t is driven by the derivative in curly theta, while curly theta is driven by the inverse derivative in theta. And this works because, well, the Hamiltonian is constant over time if you follow this differential equation. So we are not changing h a long time. That's an issue, of course, that I will mention in a minute. In most problems, or at least non-discrete problems, using this new representation has usually an immensely positive effect on the simulation, provided you can run it. This moves in a much more efficient way on the target than reversible jump, random walk, because it avoids this random walk behavior. That is, it's not going forward and backward in this perfectly random way. It has a non-reversible feature that drives the evolution on the target, and therefore has better exploration. And though, I mean, the three graphs on the left are different versions of Hamiltonian Monte Carlo with different metric that I stole from this paper by Lan, Jeremy, and courses. Of course, if you just, assuming you were able to solve these differential equations and process the Hamiltonian, there is absolutely nothing random in the picture. And so it's fully deterministic, and it doesn't change the value of the Hamiltonian, although I mean, the purpose is to simulate from this distribution. So at this stage, well, the objection is that it's not at all irreducible. That's not a simulation method. But the way to make it work is to explore for a certain time a level of the Hamiltonian, and then at random times to jump to another level of the Hamiltonian in such a way that you keep the stationary distribution. So it's a form of slice sampling in the sense that you have this target, h, you fix a value h0 of the target, you move on that level set, so imagine a big circle, and then after a random time, you go and explore another likely level of the Hamiltonian, and you keep doing that. So on one direction, or one dimension, you can be deterministic, and so it's better than being random. And that's one very naive reason for saying the words are in these methods. So because the secondary or auxiliary variable has a free distribution, there is a problem of choosing that distribution, and by default, it's most often picked as a Gaussian distribution, which is of the same dimension as the original target. And this Gaussian is centered and has a certain covariance matrix that may be the identity, which is really a poor choice, or that is derived from the target, from say an average covariance matrix, or in a more advanced feature that can be local based on the derivatives of the target one way or another. So these are the Riemannian and Lagrangian versions of HMC that appeared in the previous picture. And so in that case, once you have chosen normal, the moves for theta t and curly theta are driven by m in the first case. So theta t is understood as the speed of the move on the Hamiltonian, and then the speed is driven by the gradient of the log density of interest, which is therefore the score in that case. Okay. And depending on the choice of the metric, you may get faster moves on the target, which is a picture I stole. Well, I forgot where I stole it, but it's not mine. But the implementation is not yet provided, because you have to solve this move on the level set, and the default solution for that is to use leapfrog integration. And leapfrog integration is a discretization of the random walk that goes into 2.5 steps, where if you get back to these equations that are the standard ones once you use a normal, well, you move by a factor of epsilon from t to t plus epsilon, except that you first move to t plus epsilon over 2, following the gradient. Then you move, that's moving the speed, then you move the point according to that speed and the metric m, and then you move again the speed. And that creates an approximation to the regular equation. So you leave the correct level set, and to get back to it, you add a Metropolitan step. And you repeat that a certain number of times, and then you jump to another level step. Okay. So if you merge everything together for the quantity of interest, that's actually a form of Langevin move with scale epsilon, and theta d being the replacement of the noise in the regular Langevin. Okay. Those two, there are two parameters, therefore there is the epsilon and the number of times you will repeat the leapfrog steps on roughly the level set for the Hamiltonian. And one way to calibrate the number of steps that you make on the level set, which is represented as this curve here, is to stop when you go too far, which is an easy recommendation. You go too far if you start coming back towards your your starting point. And so that's the no U-turns version of Hoffman and Gell-Mann, where they measure when the proposal turns back, and then they pick a value on the points explored plus a completion to make it reversible, rather than fixing the number of steps. And from there you get a calibration of the proper number of steps on the level set. And no U-turn or not is one of the clogs in the STAN algorithm. And Aki will explain that much better than I this afternoon. So that's HMC in 3 minutes. I want to mention something that is a bit more current in the MCMC literature. That is an evolution in the direction of continuous time processes. Actually, there has been a fairly long literature on the use of diffusions, Langevin being an example. But it was fairly restricted to theoretical evaluations and proofs of convergence. In the more recent years, there is a slightly wider use of such methods that may become of a more practical feature of MCMC. And so that's a very quick survey of PDMP for piecewise deterministic Markov processes. That again will not get into any depths. So we have something similar to the Hamiltonian, where we have a target to simulate, and the energy of the Hamiltonian is minus log this target. And the goal is to try to get away from reversible MCMC methods, reversibility being a plus to establish that the stationary is the stationary, but meaning a loss of efficiency by coming back to places that have already been visited a bit too often, a sort of random walk pattern. And so there are arguments that I don't completely follow, that if you get away from reversibility, you should do better. Empirically, that's seen on examples. Okay. And so there is this growing literature that comes from physics, just as about everything in the MCMC world, that builds continuous piecewise deterministic Markov processes to run to a stationary, but more efficiently, apparently. And the recent literature produces stronger guarantees of convergence for these processes. So you can see the dates. It started 2009, and well, the range of the papers, at least in the statistic literature, is in this era. Okay. So there are a lot of examples where they show things work better with applications to big data I mentioned previously, but more recently you get ergodicity results and intractable targets as well. Now, point processes have been used in simulation and practically for simulation quite early, and it has been a bit ignored or forgotten in the meanwhile, but papers by Replay, for instance, have been based on jump processes. So they are like precursors of MCMC methods, that running a Markov chain in continuous time with a Markovian jump can create simulations from the target. And those are references, like the most recent one being Matthew Stevens as an alternative to reversible jump. But an earlier one that was really important but got forgotten is one by Charlie Geyer and Jesper Müller in '94. The older version of this diffusion that I followed at the time is to move according to a certain proposal and keep this value for a random time in continuous time, so it's sort of continuous weight, and make proposals that live according to their likelihood, so the product of the likelihood and the target. And to make it work, you just need to recover the detailed balance as in discrete time. So this is not something that is as natural as Metropolis hasting, but it has a fairly simple implementation that you follow a value in a time that is exponential, and the exponential parameter is this target value. The only drawback is that this may run into transience issue at a computer level, and that may be why it was abandoned rather early in the late 1990s. So if I get back to PDMP, this continuous time versions are all extending the target into a joint target, so it's the same setting as the Hamiltonian. You add a so-called velocity or momentum that is just an auxiliary variable to your current, to your value of interest x with stationary distribution pi of x, and you generate from the joint distribution following the principle that the joint as a marginalized provides simulations from the right target. So all these piecewise deterministic Markov processes have three components. That is, they are deterministic for a while, so the process evolves according to an ordinary differential equation driven by a function phi. Then something happens at some point. So there is an event rate lambda, and then at that time there is a modification of the process. So it's not deterministic. Z is changed according to a certain kernel, and then it goes again. So to run the algorithm, and here I've not mentioned yet the stationary, but to run it, you have to produce this deterministic evolution of the point zt, and then induce the random changes at this random time. And so it seems much harder to implement than, say, Gibbs or Metropolis Hastings, because you have to produce a reasonable approximation of the OD evolution, then simulate the event times, and the last point, usually not the hardest one, the modification being quite free. You may choose something that is easy to simulate from. So one of the versions of PDMP is a bouncy particle filter that has those three components you start from x, you run it for length tau, and then the velocity will change after this length tau. And the length, and that's what makes it interesting for simulation, the length of the deterministic path is driven by the energy or Hamiltonian u through the gradient of phi scalar product with the speed v. So that's the time when it stops going in one direction and changes. And it changes by bouncing, so that's the name that comes with it, reflecting on current V back symmetric around the direction given by the gradient. So you bounce and you go back. So that's the picture in the original paper. That is, you move in a given direction with a fixed velocity, and then once you get too far from the target, that's driven by this scalar product. You bounce symmetrically across the gradient to another point, and you keep doing that. And so that's a sequence of deterministic move. Instead of having points, you have the entire vector or the entire path of the process to approximate the distribution of interest on the joint pair of location and speed. And so I think the hardest part is to simulate the event times, but there are tricks in the literature, including a chapter in De Vroij's simulation book to get around this difficulty. One is a thinning that you can simulate from a faster rate and take out some of the times. So this is the idea of thinning. That is, you take out, you simulate times from a larger lambda, and then you subsample with probability 1 minus lambda over lambda. And if you can find an unbiased estimator of this ratio, you don't need to know lambda exactly. So that's thinning. You just need to find an upper bound to simulate from. And then superposition is a way to represent the rate as a sum of other rates. So again, this means that some of the terms don't need to be computed exactly, and look at the infimum of the Poisson time processes. So if you do that, you can gain and avoid computing complicated rate times. I don't know, maybe I'll stop soon, because actually the rest of it is kind of going through the literature of the recent proposals. So this is a bouncy particle filter I mentioned. There is a zigzag sampler, which I cannot avoid to mention because of this picture, where actually you zigzag because you pick one direction among 2 to the d, so the speed is just flipping one of the axes at each time there is an event, rather than going symmetric with respect to the gradient. It still enjoys the right target as is stationary, but it zigzags a bit like the slice sampler. The HMC can be seen as a form of PDMP, although that's not the regular analysis, but you follow the gradient to run the speed, and the renewal rate is constant and doesn't depend. It doesn't depend on the speed, and then you change the speed at transition according to this Gaussian that is your auxiliary artificial target. And then you may improve things a little bit in the Riemann manifold version of Girolami and Calderhead by using the Hessian in the transition target, which is this G. Otherwise, it is the same pattern. And then you have other versions where you have a choice in one direction, the other one is given by the gradient. So this reminds us of the bouncy particle. And then it keeps. I mean, it's a factory to produce different versions that have different properties that are mostly compared through experiments. So you cannot tell really which one is better. And so this is the last slide. To give you just this very crude vision of MCMC method, this last part is not very fluent. It's just to tell you that there is an existing range of research on MCMC that is currently taking place that is opening new practical perspectives to try to make things run faster. And once again, the practical run by Aki this afternoon will show you how practical it is and useful it is for real problem. So thank you.
Is there a few quick questions? Otherwise, we can talk with Charlie during the week.
Just one question about one animal that was not in your zoo. It's about gift samplers with Metropolitan steps. So I've been seeing this kind of samplers in my readings. So just what do you think about these samplers?
Yeah, so gift sampling assumes that you can simulate the full conditional. But as soon as you get into something realistic, there are some conditionals that you cannot simulate. And then it's perfectly kosher to replace any simulation from a full conditional by one Metropolitan step aiming at this full conditional. That is, assuming you can write it down for one given value, so numerically you can produce f of x1 given x2, then any Metropolitan proposal of moving x1 that may be conditional on x2, that's correct as well, will keep the join as the stationary. So if you cannot do it exactly, you can use Metropolitan. And there is no need to run several Metropolitan steps because it's not more valid or more efficient. It's just one move that you may reject and then change your component. And that's correct.